Well, hello all. It's day 3 of the lockdown coronavirus, and today we're continuing with grade 11 work, stoichiometry. Now, you might ask, why are we doing stoichiometry? Shouldn't we be doing what is at the start of the term's work, which is light passing through glass? But stoichiometry is very important, and I don't believe it's very important to your matric. This is a section you need to know very well. You don't need to carry light, the passage of light through glass at all into matric. And I'm speculating that there will be no term 2 and that we will have to abbreviate what we teach you, and we're going to have to settle for the important stuff. And this is part of the important stuff. So what is stoichiometry? Stoichiometry is the ratio in which reactants react together to form products. So let's have a look at the syllabus. So here, grade 11 chemistry, content concepts, etc. The conservation of atoms in chemical reactions leads to the principle of conservation of matter. Remember, matter cannot be created or destroyed. And the ability to calculate the mass of products and reactants. And in our last video, we learned that 1 mole of gas occupies 22.4 decimeters cubed at 0 degrees centigrade or 273 Kelvin. So if you want to convert centigrade to Kelvin, just add 273. So if 1 degree centigrade, add 273, it becomes 274 Kelvin. And at 1 atmosphere, or 101,3 kilopascals, or if you like, 1 times 10 to the 5 pascals. So there you go. That's atmospheric pressure at sea level, and that's the temperature that ice melts at. And 1 mole of gas, and what is a mole of gas? To recap, it is 6,02 times 10 to the 23 little particles of whatever gas there are. Could be hydrogen, could be oxygen, could be neon or nitrogen, doesn't matter. That if you have 1 mole of those, miraculously, they all occupy 22,4 decimeters cubed. Now, a decimeter cubed is the same as a liter. So here, I've got a pop suck. It's from a juice box. And this pop suck is 5 liters. So if we had 4 5s are 20 and a half, so I've got lots of these pop sucks. I keep them because they've got a lovely little tap. Hey man, they're free, cheap balloons. And you can fill them with water, and you can store water. Hey, maybe there's an emergency and you need to store water, so I never throw these away. I just love their taps too much. There's so many things you can do with a tap. Like I thought, you fill these little guys with water, you put them on a shack roof. When the shack catches fire, the pop suck melts, and it releases the water, puts out the shack fire. So that's another reason why I keep these things, in case I ever live in a shack. Strangely enough, 1 mole of any gas, be it neon, hydrogen, makes no difference. Water will always occupy the same volume, which is 22.4 liters. Okay, that's old stuff. Now, for today, interpret balanced reaction equations in terms of volume relationships for gases under the same conditions of temperature and pressure. Volume of gas is directly proportional to the number of particles of the gas. So what we're going to do today is we're going to have a look at, for example, we're going to first of all look at balancing an equation, and then volume relationships for the reactants and the products. Okay, so let's see some, let's have a look. What about if we have a reaction like hydrogen gas and oxygen gas react together? They're going to form something, H and O, right? And I'm sure that you guys know what is going to be formed. Well, my grade 10s are very good at figuring out the ratio in which hydrogen combines with oxygen. They go to the abbreviated periodic table. There you see this abbreviated table. It's got group 1, group 2, then it skips all the defilling transition elements, and it goes straight to what is called Roman numeral 3, 4, 5, 6, 7, 8. And they know that group 1 has got 1 valency or 1 hook. So if you if this is a hydrogen, it's got one hook. Then if you go to beryllium, here's beryllium, it's got two hooks, boron 3 hooks, carbon 4 hooks, nitrogen goes down now to 3 hooks, oxygen to 2 hooks, fluorine to 1 hook, and neon to 0 hooks. So if we ask them to combine H and O, they know you got an H with 1 hook, you got an O with 2 hooks, so you need 1 hydrogen there, 1 hydrogen there, and they're very good at hooking together things. So it's H, 2, and 1 O, because the O's got a valency of 2. And so from the group, we can tell exactly the valency, how many hooks it is. And so if we're hooking together O with H, it's going to be in the ratio of 2 of those to 1 of those. And if we're hooking H and N, now again, how many hooks has N got? There's 1, 2, group 3, Roman numeral 3 has got 3, carbon's got 4, nitrogen we go down again to 3. So if nitrogen's got 3 hooks, we need 1, 2, 3 hydrogens, so it's going to be NH3. Right, so let's go back to, so they know that the ratio has got to be of hydrogens to oxygens. They know that this formula is going to be H2O. And they know this is going to be NH3. So they know that. Let's just fill that in. NH3 is ammonia. So now we have to have rules for balancing equations. Let's suppose they are able to figure out the formula from basic principles that O's got 2 hooks, H has got 1, and they could just figure it out even if they've never heard of H2O or NH3. Right, so let's go over the rules of balancing an equation. Now the first rule is you've got to look for anything, any gas that is diatomic. Now most elements, most metals are monatomic, meaning you can have one of them, but H never exists by itself in nature. So to balance an equation, you've got to know that that's a diatomic gas, and they've also got to know that oxygen never occurs singly, it always occurs in pairs, holding hands. So we go to balance equations, we go to all the H's, that's diatomic, and we put a 2. And nitrogen is also diatomic, so we've got to also put a 2. So you'll see hydrogen, oxygen, but we're not allowed to change. We don't put a 2 after that oxygen. This, now when it's combined, in the ratio it's combined, we cannot fiddle with this ratio. It's NH3. We cannot, an H2O. That we worked out by the hooks, but to balance the equation, we've got to start with any gas that's diatomic, make it diatomic. Now we go, there's the left of the equation, there's the right of the equation. Notice that these are all gases. Now let's look. If we look on this side, we got 2 oxygen atoms. There we got 1 oxygen atom, because there's H2, there's 2 hydrogens, 1 oxygen. So somehow or other we've got to get the number of oxygens up on the right hand side. So let's try a 2 in front here, 2. So now we've got 2 oxygens, but that also, 2 in front means 2 of everything. We've also got 2 hydrogens, and 2 times 2 is 4 hydrogens. So how are we going to get the hydrogens to balance? Well, we could put a 2 in front there. We're not allowed to change what's behind when we're balancing equations. What's diatomic stays diatomic, so we put a 2 there. And now we will see we've got 4 hydrogens, 2 oxygens, 2 times 1, that's 2 oxygens, and now it's balanced. Let's have a look at this equation where hydrogen plus nitrogen go to form ammonia. Now, once we've got the formula for ammonia, we're not allowed to fiddle with that. We can only add numbers in front. Let's have a look. We got N2, and we've got here NH3. But N2 means 2 nitrogens. There's only 1 nitrogen, so we could put a 2 in front here. Let's put a 2 there. So we've got 2 ammonias, 2NH3. How many hydrogens has this got? 2 times 3, 6 hydrogens. So what if we put how are we going to get this to 6 hydrogens? 2 times 3 is 6 hydrogens. Well, why don't we put a 3 in front here? 3 H2s plus 1. We don't write the 1 N2. Goes to form 2 NH3s. So there we can see both equations are now balanced. So have a look at it. This number in front, just for the fun of it, I'm going to just put a 1. We don't normally write a 1, but there's a 1 here. And there's also, for this reaction, there's also a 1 here. So if I wanted to illustrate the ratio of the amount of gas that we would have to have 2 of these bags, 2 of those to one of the one O2 would form 2 bags full of water, gas, or steam. So you're going to need 2 volumes of this. 1 volume of that goes to form 2 volumes. So have a look at that. 3 volumes of gas goes to form 2 volumes of gas. Now look on this one, the making of ammonia. 3H2 means 3 moles plus 1 mole goes to form 2 moles. That means 4 moles of gas disappears down into 2 moles of ammonia. So all that's happening is the H's and the N's are combining together in a certain ratio, but this is the volume of gas that we're going to have. If we want to go, and this is called the Haber process, and make ammonia, we're going to have 3 volumes of hydrogen. 1 volume of nitrogen goes to form 2 volumes of ammonia gas. So 3 plus 1 goes to form 2. 3 plus 1 goes to form 2. So 3 volumes of hydrogen plus 1 volume of nitrogen goes to form 2 volumes of ammonia gas. That would be the ratio in which they would combine. Right, so let's just move this back here. So that is what stoichiometry is about. It's about the ratio in moles we normally work. So here we have 3 volumes plus 1 volume goes to form 2 volumes. We're always looking at the number in front of the molecule. So what is the ratio in volumes? 2 is to 1 is to goes to form 2. 3 plus 1 volume goes to form 2. Let's say we got 5 and liters. And we've got 5 liters of oxygen. I wonder how many liters of that we'd need. What would be, how many liters of that would we need if we have 5 of those? Well, don't we have to have double the amount? So if here we have 5 liters, here we're going to have 10 liters. So 10 liters of hydrogen plus 5 plus 5 liters of oxygen is going to form how many liters of water gas? Well, the ratio is again going to be double. So here we're going to have 10 liters of hydrogen gas, 5 liters of that, and remember the ratio is 2 is to 2, so if that's 10, that must be 10. Let's just do that again here for this one. Let's suppose for this one we have 5 liters of N2. How many liters do you think we're going to have of hydrogen? Well, look at the ratio. So anyway, if that was 5, this is going to be 15, and that's going to be 10. So 5 liters, 15 liters, 10 liters. And that's the ratio that it's going to combine. We're going to have to need 15 liters of hydrogen gas plus 5 liters of nitrogen gas will produce 10 liters of ammonia at STP. So do you see how we can fiddle around with volumes of gas and balance? Not only have we balanced the equation, we've now balanced how, and we can easily work with volumes of gas. In what ratio will they combine? So here we can see the screen just a little bit better.